Hello everyone and welcome back to Nunley Math. Thank you so much for joining us here today as we continue our discussion of pre-algebra, specifically looking at rational number conversions. This is our fourth lesson in our pre-algebra series. The first lessons we're looking at different number systems. In our last lesson, we talked about how we can change rational numbers from their fraction form into decimal form. From fraction form into decimal form. Today we're going to be doing the reverse of that. We're going to be taking decimals that are rational numbers that are in decimal form, and we're going to be putting them back into fraction form. Just as a quick reminder for you, a rational number is any number that can be expressed as a simple fraction. And as we said in our last video, all positive and negative fractions are rational numbers. We said all integers are rational numbers. We said all mixed numbers are rational numbers. We said that all terminating decimals are rational numbers. And we said that all repeating decimals are rational numbers. And we said that we know that something is a repeating decimal because we have a bar over top of the repeating portion. Just like this. We do go into much greater detail about these definitions in our previous video, so if we went through this too quickly and you're uncomfortable with this, take a second, go back and watch the video number 3 in our pre-algebra series, and hopefully you'll be able to figure it out from there. We'll spend a little bit more time on this. I do want to emphasize once again that most people are pretty comfortable with the idea of rational numbers as fractions and the different things that can be written as fractions, with the exception of this one right here, repeating decimals as rational numbers. People tend to have a real hard time comprehending that, and we're going to talk a little bit about that today and see if we can make that a little bit easier to understand. Now, because I do use these videos in my own class, I did create a couple different examples for my students to do in class as a review. What I'd like for them to do is I'd like for them to take 7/40ths, that rational number, and just like we did in the previous video, I would like for them to convert that to decimal form to keep that skill fresh in their memory. If you feel pretty confident about your ability to do this, I would recommend pausing the video real quick, changing 7/40ths into decimal form, and then restarting the video to check and see if you did it correctly. I'm going to keep right on here going, assuming that you've done that on your own. We did say that to change 7/40ths into a decimal, we have to do this as a division problem. And when we do this as a division problem, the numerator goes on the inside, the denominator goes on the outside. As with most fractions, 40 will not divide into 7 because 7 is too small, so we say it goes in 0 times. And then we add a decimal and a 0 at the end. A decimal and a 0. Because now I can say 40 goes into 70. And of course it goes in 1 time. That's a 40, leaving me a remainder of 30. When we convert fractions into decimals, we do not leave remainders. Instead, we continue adding zeros and bringing them down until we get it to either terminate or repeat. In this particular example, when I bring the 0 down, I now have 300. 4 goes into 300 7 times. 7 times 40 is 280, with a remainder of 20. Since I have that 20 there, I have to bring my 0 down again. 40 goes into 200 5 times, and there's my remainder of 0. This is a terminating decimal. 0.175 is a decimal that ends. It has a definite ending point. Now, I can convert this decimal back into a fraction if I wanted to. That's actually going to be the focus of our lesson today, but this is what we did the other day, and it's a good chance for us to talk about the relationship between the two. Again, I would recommend pausing the video and trying this on your own. I am going to continue to do these much quicker this time because this is review, just assuming that if you need to, you're going to pause. 9 divided by 11. 9's on the inside, 11's on the outside. It goes in 0 times. I add my decimals and my 0. Now I can ask, how many times does 11 go into 90? Hopefully you know it goes in 8 times with a remainder of 2. Since there's a remainder, I'm going to add another 0 and bring it down. 11 goes into 20 how many times? 1. 1 times 11 is 11 with a remainder of 9. Here's what I notice. 9, then 2, I'm back to 9 again. That's a pretty good indication that this is going to repeat, but I'm going to go again just to make sure that I have this correct. 11 goes into 98 times with a remainder of 2. So we do have this repeating pattern. 90 minus 88 is 20, or is 2. 20 minus 11 is 9. 90 minus 88 is back to 2. If I were to do this one more time, I'd be back at 20, and I'd have that 1 again. Notice, in this problem, the 8-1 pattern continues on and on and on indefinitely. I'm always going to end up with 90 minus 88, remainder 2, 20 minus 11, remainder 9, 90 minus 88, remainder. It's going to keep doing that forever and ever. And so what we do is we shortcut this and we say 9/11 is the same as 0.81 repeating. Notice that both the 8 and the 1 repeat, therefore my repeating bar should be over top of both of them. How about this? 3/22. Again, pausing the video, trying this on your own, then coming back to watch to see if it's making sense. 3 on the inside, 22 on the outside. It doesn't go, 3 can't be divided by 22, so I add my 0, put my decimals in. Insert a 0, 22 goes into 30 one time. That's 22 with a remainder of 8. Since there's a remainder, I'm going to add another 0. How many times will 22 go into 80? Well, that is 3 times. 3 times 22 is 66, leaving me with 14. Put in another 0, bring it down. 22 goes into 140. This one's a little harder because that's a big number. Let's see, 5 times 22 is 110. 6 times 22 is 132. I think it's going to be a 6. Leaving you with a remainder of 8. Notice you started with a 3, you then had an 8, then you had a 14. Now you're back to 8 again. If we're lucky, this is going to start repeating. 22 goes into 80 3 times. 3 times 22 is 66. And that's going to leave you with a remainder again of 14. Notice what's happening here. We've got 3, then 6, then 3. This is going to be a 14. We'll bring down a 0. It's 140. We're going to get another 6, and it's going to repeat. The 1 only occurs one time, but this 3, 6 pattern is going to keep showing up over and over again. So if we wanted to write this, we would say this is 0.136, and then we would use the repeating bar over top of both the 3 and the 6 because both of those do repeat. Now I know we did this very quickly. That's primarily because you should already be comfortable with this and working it out on your own. If you're not, go back and watch video 3 in this series on the conversion from fraction form to decimal form. That will help you quite a bit. That's not our focus for the lesson today. Here again, this is just review for those in my class to make sure that their skills are fresh. For today, our goal is to convert between fraction form and decimal form and fraction form. Decimal form to fraction form. And we're going to start with those decimals that terminate, those decimals that end, like 0.8. We like these. These are really easy because if we realize how to say 0.8 using its correct name, we should know that 0.8 is actually the fraction 8/10. And so it's very easy to write it as a fraction. If we use the right name, terminating decimals always give us a fraction very easily. And then all we have to do is put the fraction into simplest form. Now, notice I did this divided by 2/2. This is one way of simplifying fractions. Simplifying fractions is not our focus today, so I'm not going to spend a whole lot of time on this. If getting from 8/10 to 4/5 is a problem, probably you need to go back and watch a video on that. But I do want to take a point and emphasize that this can be divided by 2/2 because 2/2 is the same as a 1. And the identity property, or the multiplicative identity, says I can multiply and divide by a 1 anytime I want. This is actually pretty straightforward, pretty simple if you understand simplifying fractions. Check this out, 0.72. Do you know the right name for that? Well, let's see. The 7 is in the tenths place. The 2 is in the hundredths place. We always name it based on the hundredths or on the last digits place value. So this is going to be 72 hundredths, or 72 over 100. That simplifies to 36 over 50 and 18 over 25. Again, simplifying fractions is not what we're primarily focused on here today. If this is the problem, then that's the video you're going to want to go back and watch. 5.015. 5.015. If I'm reading this properly, this would be 5, this would be and, this would be 15, and I would name it based on the farthest to the right place value, tenths, hundredths, thousandths. This is 15 thousandths. 15 thousandths. 15 thousandths. And if you want to go ahead and put the 5 over here as well, you can. I usually stick it in at the end. 15 thousandths, notice the top and bottom can both be divided by 5, which is going to make this into 3 over 200. Again, don't forget, it's 5 and 3 200ths. Terminating decimals are pretty straightforward, I think. Don't let it throw you off if I stick a negative sign in front. All that means is when you're finished, your fraction is going to be a negative. I would read this as 0.128, or more correctly, 128 tenths, hundredths, thousandths. This is negative 128 thousandths. Negative 128 thousandths. If you were to simplify that, again, ignoring the negative, we're just hanging on to it, I could divide the top and bottom by 2 and get negative 64 500ths. Divide by 2 again and get negative 32 250ths. And I can divide it by 2 again and get negative 16 over 125. The point here being that every decimal that terminates can easily be written as a rational number in fraction form. Terminating decimals ought to be very simple for us if we know how to read decimals appropriately. Here's the tricky part. What if I have a repeating decimal? Repeating decimals require a whole lot more work. In my opinion, this is one of the more difficult things we have to learn in number sense, and in fact, in most classrooms, they're not even going to bother to teach this anymore because most people are going to look this up on in a table or look it up on a calculator. I happen to teach an advanced algebra class and an advanced 7th grade math class or advanced pre-algebra. So I like to challenge my students sometimes to try things that are just a little bit more complicated than we would expect in a regular pre-algebra class. And this is one of those times where we want to stretch this out just a little bit because our standard in 7th grade is for students to understand what is a rational and irrational number. And as I said on the very first slide, students really struggle with this idea that repeating decimals can be written as fractions. And so to me, rather than just repeating that over and over again, it seemed to make more sense simply to show them how to do it. I'm going to walk through this process with you. This is, I'm not going to lie, a bit of a struggle. You're probably going to need to watch the video a couple times. I have some examples here. I've got some examples on another slide as well. But you're really going to want to watch these pretty closely because this does become just a little bit tedious. Let me walk through this with you. The first thing we're going to want to do is take the repeating decimal and set it equal to x. Set it equal to x. There's my repeating bar. Now, I can't do a whole lot with this as long as it's in that repeating bar form. So I'm going to go ahead and write the number using the ellipse. The ellipse just means I'm going to write it repeating a couple times and then use this symbol right here, this ellipse, to show that the pattern's continuing. I just don't feel like writing anymore. Does that much make sense? We're changing it from repeating bar notation to ellipse notation. And then I'm going to do something really cool. I'm going to determine how many places to move the decimal so that one iteration of the repeat is to the left of the decimal. That sounds much more complicated than it is. Let me show you what I mean. Right here, I have a 7 and a 7 and a 7 and a 7. The 7 is repeating, but all of the repeats are on the right side of the decimal. I want to move that decimal so that one of them is on the left. I'm moving the decimal so one of them is on the left. Anytime I move a decimal one place to the right, I'm really multiplying by a 10. So since it's a move one place to the right, I'm just going to multiply by a 10 to the first power. And I'm going to rewrite this as if 1x is 0.7777, 10 x's would be 7.7777, on and on repeating. You might want to pause the video and look at that really quickly because this is really the place where people struggle. My decimal is to the left of all my repeats. I need to move it so that exactly one copy of the repeat is on the left side of my decimal, or so the decimal is on the right of one of those. That's a move of one decimal place. Anytime you move your decimal one place, you're multiplying by a 10. Since I'm multiplying by a 10, I'm really going to multiply this side by the 10, that's 7.7777, and I'm going to multiply this side by a 10. That's where I get my 10x. Does that make sense? Now, some people get freaked out by the fact there are 5 7s here, but there are only 4 here. Remember, there's actually an infinite number of 7s. I just chose to write one extra. If you're comfortable with that, that's the hardest part of what we're going to do. The next thing I'm going to do is I'm going to write the original equation underneath this one, making sure I line up the decimals and the equal signs. I'm going to take this right here and I'm just going to rewrite it down here so it looks like this. Take a second and compare those. I brought this down exactly as it was. The first one is times 10. Are you good with that? This is the thing that I think is really cool. I'm going to go ahead and subtract these two equations. When I subtract those, the left side says 10x minus x, which is 9x. The right side says 7 minus 0 is 7. 7 minus 7 is 0. 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 Did you see what just happened? By doing subtraction here, I'm infinitely going to be able to subtract 7 minus 7s because these all line up. And they're all going to become zeros. 0, 0, 0. I have taken my, erase this, I have taken my repeating decimal and I've gotten rid of all the repeats by subtracting them away. That, to me, is very, very cool. So here's the last step. If you've done a little bit of simple equation solving before, you can identify this as a single-step equation. 9 times x equals 7, and you can use the property of equality to solve that. Now in my class, my pre-algebra class, my students aren't really familiar with that as much as I would like them to be. It's kind of a new concept for them that we're introducing in 7th grade. They may have done a little bit with it in the past, but most of them aren't real comfortable with that. So what I tell them is the next thing they want to do is just divide both sides by whatever's with the x. When they do that, 9 divided by 9 becomes a 1. And on the right, you have the fraction. 0.7 repeating is the fraction 7/9. I think that's pretty cool. If you're not sure, take a calculator and do 7 divided by 9. You should get 0.7 repeating. Your calculator may round it off to an 8 at the end, but it is 0.7 repeating. Now, I realize that this is not one of the simpler things you've done. This is going to be just a little bit tricky. So I am going to do a couple different examples of these, and you're probably going to need to watch this a couple different times for it to make complete sense and to get comfortable with it. But once you get it, it is kind of fun. I think these are really cool. I'm going to take, for this next example, the 0.64 repeating, and I'm going to write it down. And then I'm going to change it from bar notation or repeating bar notation to ellipse notation, where I just write a couple iterations or a couple copies of the 64, and then I put my ellipse sign. Notice we set it equal to x, we wrote it with the ellipse. Here's the trickiest part. We want to figure out how many places we need to move this decimal in order to get one copy of the 64 on the left side. I want one copy of 64 to the left. Well, my decimal is going to need to move here for that to happen. That is 2 decimal moves to the right. So I'm going to multiply both sides by 10 squared, or multiply both sides by 100. I'm going to multiply the left by 100, and I'm going to multiply the right by 100. Notice it was a 2 decimal move, so I have to multiply by 10 to the second, or 100. And that gives me 100x equals, since I moved the decimal 2 places, it's 64.64 repeating. There again, don't worry that there's more 64s because there's an infinite number of them. I'm just choosing to write a couple extra this time. Once I've done that, I'm going to take the original equation and bring it down here. So this original equation is going to come all the way to the bottom, and I'm going to line it up. That's the worst arrow I think I've ever drawn. There you go. I'm going to line it up. I line it up so that my equal signs are lined up. I line it up so my decimal points are lined up. And then I subtract. Notice on the left side, 100 minus 1 is 99x. Over on the right, 4 minus 4 is 0, 6 minus 6 is 0, 4 minus 4 is 0, 6 minus 6 is 0. 4 minus 0 will be 4, 6 minus 0 will be 64, and you end up here. Again, my students aren't great at solving equations yet. It's a new concept for us this year, so I just tell them, divide both sides by 99, and you get 64 99ths. Now, I would encourage you to, at this point, pause the video, read through the notes again, and I suggest you try that 0.51 on your own, and then restart the video to see if you're understanding this or not. I'm going to go ahead and keep going under the assumption you have already done that. I set it equal to x. I then change it to ellipse notation. Notice I did 2 repetitions, but you could do 2, 3. It doesn't really matter as long as you're consistent. And then I'm going to look and see how far that decimal is going to need to move to get one example on the left of the decimal. It is a 2 decimal place move, which means I'm going to multiply by 10 squared, which is 100. That means I'm going to multiply the left side by 100. I'm going to multiply the right side by 100. And that's going to give me this. Notice now one of the 51s is on the left. I bring the original equation down, and I subtract. Once again, notice these are lined up. 1 minus 1 is 0, 5 minus 5 is 0, 1 minus 1 is 0, 5 minus 5 is 0. You're left with 99x equals 51. Divide both sides by 99, and there is your answer. Now, I believe, unless I'm mistaken, that does also simplify down to 1733 if you divide the numerator and the denominator by 3. Again, that's not the focus of the lesson here today, so I'm not going to spend a lot of time on that. I just wanted to make sure that you were aware. I think that equal sign will appear. There you go. I need to switch the order on that. What do you think? Is that easy or hard? Again, I find this to be confusing. In my class, we would spend a couple of days doing this because it does take a long time to get used to, but it does illustrate the fact that no matter how complicated this gets, if it has a repeating bar, it can be written as a fraction. Let's do some more. These are a little bit different. You'll notice on the previous slide, to the right of the decimal, you always had a number that repeats or multiple numbers that repeat. But on this slide, it's slightly different. You've actually got a gap here before the repeating begins. You've got a gap here before the repeating begins. You've got a larger gap here before the repeating begins. That's going to change things just slightly for us, but big picture, it's going to work out very closely to the same way. Here's what I'm going to do. I'm still going to set the decimal equal to x. I'm still going to write it in ellipse form. Notice I went ahead and wrote several iterations of the 7. Again, it doesn't really matter how many I leave. I always like to have at least 3 or 4 written down for when I line up for my subtraction. I'm still going to determine how many places to move the decimal so that one iteration is to the left. In this case, that's 2, which means I'm going to have 10 squared, which means I'm going to be multiplying it by 100. Again, none of this is any different than what you've done before, except that I'm running out of room. Is that good right there? 100, 100, there we go. That much is all the same. But my next step is going to be slightly different. In the next step, I'm going to look back at this original equation, and I need to determine how many places to move my decimal so that the first iteration is immediately to the right of the decimal. In other words, I need my decimal to be right in front of the first repeat. Right in front of the first repeat. Okay? How many moves would that have been? Well, that's just 10. That's a move of 1 decimal. I'm going to multiply through this original equation. Instead of by 100, I'm going to multiply through by 10 in order to get my repeats right next to the decimal. Notice that once again, this is all lined up really nicely for me to subtract. 7 minus 7 is 0, 7 minus 7 is 0, 7 minus 7 is 0, 7 minus 7 is 0. Notice that I get 90x equals 7. And just like before, I'm going to divide. The answer here is 7/90ths. 7/90ths. I think that's kind of cool. Again, the only change is that this bottom equation is not just going to be a 1x like it was on the previous slide. We're actually going to have to move the decimal for the first equation by multiplying through by 100. We're also going to have to move it through by for the second equation in order to multiply through by 10. Again, you want one repeat or one iteration of the decimal to the left. You want the first iteration immediately to the right. That's how we're going to set those up. Little bit tricky. You may have to watch this a couple times to get that down, but once you get it, I think you're going to enjoy this. Here's another example. If you feel pretty confident, I'd recommend trying this on your own by pausing the video. Obviously, since you guys are watching this, I am not going to stop. I'm going to keep right on going. So, you know, feel free to turn it back on and listen once you've got yours worked out. As always, set the decimal equal to x. Write it in ellipse form. Ellipse form. There again, I've just written another example of the repeat, and there's an infinite number of them, so I can write as many or as few as I want. Just like before, I'm going to count how far I need to move that decimal to get one example of the repeat on the left side. That was a move of 3, which means I'm going to need to multiply through by 1,000. 1,000. So I'm going to multiply the left side and the right side both by 1,000. Obviously, I cannot write with a mouse. Wow, that's awful. Now you know why I type everything. I'm going to multiply through it by 1,000 and get 1,000x. Notice the decimal moved 1, 2, 3 places. Next, I'm going to see, my eraser, that's all in the way. It's getting kind of mucky up there. Next, I'm going to see how many places do I need to move my decimal so that it is immediately to the right of my decimal. So the first repeat is immediately to the right. Since 24 is my first repeat, I want it to be right here. That's a move of one place, or 10 to the first. You can see I forgot to fix that. 10 to the first. If I multiply both sides by 10, I get 10x equals 0.2424. Again, the reason I do that is I want these to line up for subtraction so that 4 minus 4 is 0, 2 minus 2 is 0, 4 minus 4 is 0, 2 minus 2 is 0, 24 minus 0 is 24, 1,000 minus 10 is 990. And just like before, division gives us our answer, 24 9/90ths. If you've got a keen eye, you may have also recognized that will simplify to 8 over 330. And if you have a really keen eye, you might also notice that both of these can be divided by 2. This is 4 over, I believe that's 165. 4 over 165. I'll have to add that into my slideshow. And there you go. Last one, again, pause it if you feel confident you want to try it. I'm going to do this one a little quicker. There's my repeat. There it is using the ellipse. I need to move it 4 places to get one example of the 17 on the left side. That's going to be 10,000 x equals 17.1717 because it's 4 places. Almost messed that one up, didn't I? 10,000. 2 and 3. I then need to start again. I want to move my decimal so the repeats are immediately to the right of the decimal. That's a move of 2 places. 2 places, which would be 10 to the second. That's multiplying by 100. Now, I'm still going to subtract. Probably there's going to be an error here because this should be 10,000 minus 100, which means this should be, what, 9,900? X equals 17. And then, of course, we would divide both sides by not 900, but 9,900. That is really hard to write. And you would get 17 over 9,900 as your fraction. Again, if you're not convinced by this, you can certainly go ahead and type that into a calculator and you'll see that it does in fact come out. Hopefully this has been helpful to you. I realize this is a difficult concept to get. I would suggest that if you're still struggling that you take a break, you go back and start again from the beginning. I think you'll find that it will make a whole lot more sense after you've done that. As always, take some time to leave us a comment in the comment section if this was helpful to you. Make sure that you smash that like button. Go ahead and subscribe so you can follow along all the way through Algebra 1, and certainly make sure you turn on the notifications so that when we put up something new, you'll be right there with us. As always, thank you so much for your time and attention. We appreciate it. Appreciate all you guys. Take care of yourselves. Bye-bye.